In this section, we're going to talk about the electrical voltage. We will start describing what work and potential energies are. We will talk about forces between charges. We will introduce electric fields. And finally, we'll be able to define the voltage. Let's try to define work. When I say work, I don't mean like a job, but I mean the definition that a physicist will give you. So work, as defined on the left, is done on an object when a force acts on it in the direction of its motion. So this definition is probably not super intuitive, so I come out with a little drawing here on the side to explain it a little bit better. Let's say there's a person here, and this person wants to push an object with a certain mass, and he wants to push the object in this direction. Now, what the person will do will push, so will apply a certain force, F. This force will be in the direction of the motion, obviously. And after a while, the person hopefully will be successful and move the object from that initial position to another position at a certain distance L. Now, in this very simplified example, the work that a person has done, which I'm indicating with W, is equal to the product of the force multiplied by the distance. So the unit of measurement in this case is Newton, which is the unit of measurement always used for forces, and meters, which is obviously for the distance. This unit of measurement is also equivalent to joule. Now that we understand what work is, we can talk about potential energy U, which is the capability of a force of doing a work which depends on position or configuration. This is really the key. I have a little example here to understand it better. Let's say you have a ball of a mass m. It could be really any object with a mass that at a certain time 0, it is at a certain height h. Now we know that every object with a mass is subject to the force of gravity, a force that will take the object, push it down, and bring it to the ground. So after some time, at a time t, the object would have gone from the height h to the ground, so height equal to 0, for example. According to the definition of potential energy, at the time 0, the object has a potential energy equal to F multiplied by h, because in that moment, just because of the position of the object, so here how we connect to the definition, just because of the fact that the object is elevated from the ground, the force of gravity F can act on it and do a certain work. Remember that you have work when the object moves in a certain direction and there is a force applied to it in the same direction, which is the case in this example. At time t, the object is on the floor, there is no net force applied to the object anymore, and the object and also the height is 0 now, so the potential energy is 0 in that case. Work and energy, as you can see, are interchangeable in a way, so they're both measured in joule. One thing that is really important to highlight for potential energy is that the potential energy of an object is not an absolute value. So, for example, in this case, we say that when the object is, the ball is at a certain height h, the potential energy is exactly F multiplied by h. In reality, it is possible to demonstrate that every potential energy is defined plus minus a certain arbitrary constant. As long as we apply the same constant to all the other potential energy in the system, everything works. But what does it mean? This sounds a little strange. Now, the energy could be any value. What I'm trying to say is simply that the only things that really matters, the only thing that really has a significance is the difference of energy. For example, between time 0 and time t, the difference of potential energy between the ball is always going to be equal to F multiplied by h. Doesn't matter what is the constant that we add, because when you do the difference, the constant will be simplified. So saying that the ball has energy equal to 0 on the ground, it's perfectly fine, but it's just an arbitrary convention. This is something really important to understand, because potential energy is intimately related to voltage, and the same concept, exactly the same concept, also applies to the voltage. When you say that in a certain point there are 3 volts, in reality, all you're saying is that in that point, there are 3 volts more than some other point. It doesn't really mean that that point is exactly absolutely 3 volts. It's simply the difference relative to another point of the circuit. We are almost ready to explain what voltage is, But before that, few other simple concepts. So the first is shown here to the right of the slide. Don't read the text for now. This is very simple. This drawing is simply showing something that you probably already know, which is that charges of the same sign repel each other. So whether they are both positive or also both negative, there will be a force that pushes them away. And by the way, this force is called Coulomb force. Whereas if the charges, they have different sign, they will attract each other. This is all nice and easy, but there's probably a question in your mind. It certainly was in mine. How does this charge know that there is another charge Q with the same sign of the charge, so that a certain force F is going to be applied to it, depending on the distance d between the two charges? This is an important concept because as human beings, we use that if you want to communicate something, you have to emit some sort of signal. Audio if you talk, video if you wave your hand. But here, that's not the case here because charges don't have ears or they don't have eyes. So how do they communicate? Well, to explain this phenomenon, physicists introduced the concept of electric field. Every charge emits electric field in all directions around them. You can think of the electric field as a sort of a sound wave. Just as a sound wave, the intensity of the field is higher close to the charge and becomes lower and lower as you go away from the charge. The electric field will spread at infinite distance, but obviously at some point it will be really tiny. And the other charge Q, depending on the relative distance between the two charges, will fill a certain electric field, and depending on the intensity of the electric field in the position of the charge Q, it will be subject to a certain force F. So electric fields are used by charges to feel the presence of each other and reacting accordingly to Coulomb's law. Let's try now to understand what is the connection between electric field and potential energy that we'll now call electrical potential energy because we're talking about charges. The picture here is a similar example as before. We have two charges, Q1 and Q2. For Q1, I show the electric field, which is emitted radially by the charge. The electric field is indicated with E. There is a little arrow here just to indicate that in any point of the space, it's not enough to tell the value of the electric field, but you also have to indicate what is the direction of the electric field. And then we have Q2 here, which will fill the electric field. The intensity of the electric field that Q2 will fill depends on the distance r. The higher is the distance r, the lower is the intensity of the electric field. Q2 will be subject to a certain force F, which depends on the value of the electric field where Q2 sits, multiplied by Q2. The force F applied to Q2 will push Q2 away and will do a work on Q2. Because again, there is a movement and a force in the same direction of the movement. So because there is the possibility of a work to be done that arises from the relative position of Q2 and Q1, we can say that Q2 has a certain potential energy. To summarize, a charge in an electric field has electric potential energy because work can be accomplished by the field via Coulomb forces. Similarly to the example before, where the ball had lower energy when it was on the ground, in this case, Q2 will have lower energy if it's very far away from Q1, because the intensity of the electric field is very small. Some work can be done, but it's a very small work. Whereas if the two charges are very close to each other, they have a lot of potential energy because the work that can be done is greater. It is possible to demonstrate that the potential energy of the charge Q2 can be written with this equation. So U is equal to K, which is a constant, multiplied by Q1, Q2. So it depends on the value of Q1, obviously, because the higher is Q1, the bigger is the electric field. It depends on Q2 because the bigger is Q2, the bigger will be the force. So the bigger will be the work that will be done. And it also depends on R, on the distance, because the smaller is the distance, for the same value of the charges, the higher will be the electric field in the position of Q2. We can finally talk about voltage. Voltage is electric potential energy per unit of charge. So in the example before, if this was the equation of the potential energy for Q2, the voltage at Q2 at the position of Q2 will be equal to K, which was a constant, Q1 divided by R. So you see it's simply the same equation, we just eliminated Q2. The voltage is a more convenient way to talk about electric potential energy in electrical circuits, but it's intimately related to the electric potential energy. Voltage, as you certainly know, is measured in volts, and the symbol of volts is capital V.